My name is Aviv. I will be moderating this session. And the first speaker of this session is Velich. He will present Learning Differential Invariance of Planar Curves. It's a work with Kimmel of the Technion.
Okay, hello everyone. My name is Velich. I'm a graduate student of Professor Kimmel in the Technion, and I will present my work on learning differential invariance of planar curves. So a bit of background and motivation. So consider you're given a jigsaw puzzle. How will you devise a method to solve the puzzle? How would you analyze the boundary curves of the puzzle pieces and extract their local properties in order to build your method to solve the problem? And even if you solve the problem, how would it generalize to a distorted domain? So let's say I now distorted my domain with some random linear transformation. Would you still be able to solve the original puzzle with the original pieces just in this domain? Or take it from a different direction. Let's say I give you two boundary curves of a butterfly, which is laying on some wall, and you took an image of this butterfly from 2 points of view, and those are the two boundaries that we see here in red. If I give you these two, would you know if those two boundaries are a butterfly or even the same butterfly? How would you devise a method to solve those problems, which are known as equivalence problems of symmetry groups? And differential invariants are mathematically proven to provide a complete solution to those equivalence problems. So what are differential invariants? So for example, we have those two curves here on the left and the right. Both of them are known as Euclidean equivalent curves, and we intuitively know that the Euclidean curvature at two corresponding points, P1 on the left and P1 on the right, will be the same. We also know intuitively that the arc length, Euclidean arc length between two corresponding points will be the same. So the distance between P1 and P2 is the same as the distance between P1 and P2 on the right. So if the curvature and the arc length are two invariant properties with respect to the Euclidean group, we can also know or say that the derivative of the curvature with respect to arc length will also be an invariant quantity. So it happens that it also true, this theory, or it generalized to other transformation groups, or less restrictive transformation groups like the equivalent transformation, which we see here, which is an area-preserving transformation. It happened to be that there is something called the equivalent curvature and the equivalent arc length, which are invariants with respect to this transformation, and therefore there is also the equivalent derivative of the curvature with respect to the equivalent arc length, which is also invariant. And going on, it's also true for a general affine transformation and even to a general projective transformation. So the fundamental theorem of differential invariance states that every transformation group G that acts on the plane on R2 in our context admit two local G invariant properties, which we call differential invariants. And the first is the G invariant curvature at a point, which we denote by kappa. And the second is the G invariant derivative of the curvature with respect to arc length, which we denote by kappa subscript S. So what we can do with those differential invariants, so if we plot the kappa S as a function of kappa at each point along two equivalent curves, we should get exactly the same plot. And this plot is known as the signature curve of some curve, and if two curves are equivalent with respect to some transformation group, those two curves should be identical theoretically, so for example, Hausdorff distance will be 0. So using those signature curves, we can evaluate whether two curves are equivalent with respect to some transformation group. So if you want to now numerically approximate those invariant properties, those differential invariants, for example, the curvature, we will hit some problems when we try to take the approach of the axiomatic approach or the finite differences approach. Well, while the Euclidean curvature can be numerically approximated in a stable manner, the equivalent curvature is a bit more problematic. It has inherent instability because, as we see, the equivalent curvature, the expression for the equivalent curvature has the second derivative at the denominator, and therefore at inflection points it will explode. And it happened that we won't be able, for example, to approximate stable, numerically stable signature curves for curves which are not convex, for example. So what we want to do? Well, what we want to do is to try to devise neural models which will approximate those local properties, those differential invariants, with respect to some transformation group. So we want to build a differential invariance learning environment which, given some transformation group G as an input, it will give me a neural model which will approximate the G invariant kappa and kappa S at a given point. So how we are doing it, what is our approach? First, we need to generate a large data set of planar curves. We do it by just taking some raw image. We turn it into a grayscale image, we blur it, and then we extract some level curve at some arbitrary intensity. And we do it on tens of thousands of images from the internet, and we get virtually unlimited data set size of planar curves. So now that we have this data set, we designed the Siamese network, a multi-head Siamese network, fully connected, that will approximate the kappa and kappa S at a given point on a curve. And how we train this network? Well, we train it in a self-supervised manner with training tuplets which are built from anchor positive and negative examples. So we use contrastive approach. So for example, given how we build the anchor examples, so you have to look at the upper row here. So we just draw some planar curve, random planar curve, take some random point on this curve, and we downsample this curve because we want our network to be not biased to specific sampling scheme, and it also means that we have to be invariant to reparametrization of the curve. So we take a local neighborhood around this point P, we put it in some canonical form, and we feed it into the network, and what we get at the output of the network are a vector in R2, which is we interpret as kappa and kappa S at the given point, the curvature and the derivative of the curvature with respect to arc length. So we do the same thing for the positive example. We take the same point just on an equivalent curve. So the curve of the positive example was transformed by some random transformation of some group G, of which we want to learn to approximate its differential invariance. So these are the anchor and positive examples. In order to build the negative examples, we just take random points on different random curves, and that's how we do it. These are, we have M negative examples. We can set M to whatever we want. It's some kind of hyperparameter. And now, what is the loss? We have two losses here. Well, the first I call it the invariant loss, invariance loss, which is some kind of contrastive loss, which we wanted to minimize the distance between the anchor and positive examples and to maximize the distance between the anchor and the negative examples. That's what will make our network to really learn the differential invariance, those local invariant properties. And we also have an orthogonality loss, which force kappa and kappa S that our network learn to be orthogonal, because kappa S is a derivative of kappa. So they should be orthogonal, because if, for example, kappa represents the position of some steering wheel of a racing car, then kappa S is how fast I move the wheel left and right. And those two quantities should be uncorrelated. So basically, we minimize the absolute value of the Pearson correlation coefficient of our approximations for kappa and kappa S of our training tuplets. And okay, so after we train the network, now we have a trained model, and we evaluate. I show now some qualitative evaluations of the model. So for example, at the top row here, we have some input curve, this colorful curve. The second row is the network approximation for the curvature, the affine curvature in this case, at each point. The third row is the approximation of kappa S at each point. And what we see at the bottom row is the signature curve. It's the plot of kappa S as a function of kappa. And what we can see here is that between two extremum points of the kappa S, we have an extremum point of kappa. So kappa S is really a derivative of kappa. That's the interpretability of what our network learned. So to evaluate the group invariance of our model, we evaluate the affine curvature of two equivalent curves, what we see here in red and blue, for example, this animal head. And we can see that really when we evaluate the signatures, we get matching signatures when we plot the red on the blue, and also for the curve on the right. This means that our network really learned the true, or something that is correlated with the curvature and with kappa and kappa S at the point. And we also want to evaluate the reparametrization invariance of our network, or its robustness to different sampling schemes. So for example, on the left we have this butterfly, colorful butterfly curve, which we approximate its kappa and kappa S at each point. We get those signatures as we see here, and then on the right is the same curve, just when it was transformed by some random affine transformation, and also downsampled by 40%. So we removed 40% of the points non-uniformly, and we still see that the network could learn and plot the signature, which really resembles the signature of the curve on the left, which is which is the original one without downsampling. You can see that the colors, the peaks and the valleys, match the same colors both on left and right. And we also show that our method is superior over axiomatic approaches. So for example, on the left, we approximate the signature curve of two equivalent curves, the red and the blue. And on the right, we approximate, on the left is using our model, on the right is using the Euclidean, the axiomatic or finite differences approach to approximate the Euclidean signature curve of a curve. And we can see that on the right, the curves, the peaks and the valleys also don't match, and also the blue signature is much more amplified with respect to the red one. They do not really match, while our signature really sits one on top of the other. So we also make a quantitative evaluation. So what we did is we took a collection of silhouettes of different items, for example, poses of some basketball player, some clouds, some dogs, some birds, all those kind of things. And we extracted the boundary curve of each of those silhouettes. So we got a collection of planar curves, which we use as a benchmark. And what we want to do is, for example, take a curve, or for example, in the basketball case, we take some pose. We take the boundary curve of this pose, we transform it, downsample it, and then evaluate the signature of this curve on the scatter curve on the left. And we use this signature to try and see if we can now match which is the original silhouette which we used to generate this curve on the left. And we do it for each one of those silhouettes. So if we have 30 silhouettes, we have to match the correct silhouette out of 30 possible items. And we show that our signature can do it with a success rate of around 80 or 90% under a downsampling of around 30 or 40% of the points. And in my opinion, it's quite impressive. And if you compare it to the axiomatic Euclidean signature curve, it's much, much better. The axiomatic signature gives less than 3% success rate. So what our future research, we want to take this approach and to generalize it to higher dimensions and to approximate differential invariance of points on two manifolds or surfaces embedded in R3 and see if we can generate invariant signature of surfaces and use it for shape analysis of point clouds and 3D shapes. And that's it. Thank you.
Thank you, Roy. We have time for a single question.
Thank you. The question is how those signatures could change or be affected by, say, some addition of noise to the curves. Because if I would think about practical use of such things as a descriptor, so I would like to be robust against noise and to be able to match.
Yeah, so you are talking about noise which is not reflected in the sampling scheme, but of the coordinates of the points.
Of course, so something which is not lie in the group of transformation, something
yes,
quite
I understand.
different.
I did not experiment with this, but one thing that I can take quick now is that you can just try and smooth the curve and then approximate the signature, and maybe this will give you something which, when you evaluate the Hausdorff distance of the two curves, of the signature curves of the two curves which we want to compare, you get something good enough with respect to other curves. But it's true that it requires some experimentation.
Thank you. Let's thank the speaker again.